everybody, thank you guys for coming to our SOLIDWORKS plastics and flow simulation training event. The purpose of it is to ask the question, have you ever looked at a custom tap handle and wondered how would I manufacture that? What's the best angle that I should pour my beer out into? We really take a look at those questions and then answer them using our analysis programs within SOLIDWORKS. So we're going to start with SOLIDWORKS flow simulation and look at how to run a transient fluid flow optimization and look at many different angles of that beer glass. And then inside of plastics, we'll look at how to design a mold, look at sink marks, simulate overmolding, and have a little bit of bonus time to discuss SOLIDWORKS Visualize and 3D printing if you have any questions. Getting started with SOLIDWORKS flow simulation. First off, why do we tilt the beer glass? It's to prevent the beer from tasting like this. But really, what's the science behind it? What's causing it to taste bad? Well, when we fill a beer glass at a bad angle, what we're doing is creating air pockets or nucleation sites. And these nucleation sites have carbon dioxide that mixes with the beer that then creates foam. If you have just enough foam, it holds in the carbon dioxide in the glass. If you have too much foam, the beer tastes flat. So, what is the best angle to tilt that beer glass to produce a minimal amount of air pockets until we actually want them? I went and did some research. To fill a beer glass, the types of analysis I'm going to need is transient fluid flow and a liquid-gas interface between the beer and the air. That, to me, sounds like SOLIDWORKS flow simulation, which does computational fluid dynamics. Of course, it does results like pressure drop or stagnation regions or velocity paths. It can do shear stress on surfaces or reaction forces like drag. It can do temperature distributions on an assembly due to conduction, convection, or radiation. And it can do rotating parts like this impeller. So let's go ahead and take a look at the math behind it, just to understand free surface flow, that liquid-gas interface, and the assumptions that we're making. So SOLIDWORKS uses what I'm calling free surface, what SOLIDWORKS calls free surface, to represent the boundary between a liquid and a gas, essentially two immiscible, non-soluble fluids. Mathematically, it uses a volume of fluid technique, where essentially each mesh cube in SOLIDWORKS is assuming the volume fraction is equal to 0, and there's a ratio of the different fluids inside of that cell. Now that's just the math. How does that actually apply to us in simpler language? Well, according to the volume of fluids technique and the code that we have applied in SOLIDWORKS, we can only do liquid and gas together in the same domain. That means no real gases or non-Newtonian fluids, for example. Second, we're not doing more than two fluids. Third, and this is constant throughout SOLIDWORKS, it's not something specific to free surface, we can't do phase transition. For example, droplet formation in a humid environment, or the freezing of a fluid into ice or melting, for example. Now, there are ways around these things. I just say these specifically as watching the formation of droplets we are not doing. So, in terms of that, and then taking it over to examples, water in a tank, for example, dominated by inertial forces, like the sloshing example that we see on the right-hand side. Other examples like filling up a tank or emptying a tank, or continuous jets of fluid like through a hose. Other examples, energy propagation, like in wave formation, or dam overflows, or wave formations near ships and vessels causing drag. And like I said earlier, we're sticking with low surface tension, so no droplets or air bubbles, but anything with a low surface tension works well here. Now that we have that, let's go ahead and set up the analysis inside of SOLIDWORKS flow simulation. I went and did some research on how long it took a pint glass to fill, and that was about 7 or 8 seconds, which rounded up to about 1 gallon per minute. I am rounding up here just for speed in the calculation, just to keep the number simple. So starting with the main setup, this is just an assembly file made up of part files and held together with mates. I'm going to end up simulating the beer glass at different angles. So I have an angle made here representing that shifting. Once I have the assembly set up in the way that I want, I go to my SOLIDWORKS add-ins, turn on my flow simulation add-in, and get this command bar. I've been using flow simulation for many years now, and I still always start with the wizard. It has about 8 steps, and I just kind of go through this by hitting the next button. So this first step here is unit system, and earlier in my PowerPoint I talked about gallons per minute being my flow rate. I can override these default units under the loads in motion area and go into volume flow rate and change that from meters cubed per second to gallons per minute. Now I point this out because, hey, it's really cool to have such a big amount of options for units, but I also want to say that there is custom units here. And I point this out because flow simulation is extremely customizable, and I find that so amazing. So I can customize anything we're going to keep seeing in the rest of this setup, like fluids, like the result plots we're looking at, and many other things besides. So just keep that in mind, very customizable. Now we get to our next panel. This is the meat and potatoes of the wizard. Now, am I going to choose internal or external? This is airflow in a giant room around the glass. There's no bounding box kind of containing all that air. So we consider this an external study, just airflow in a general space. Next, what do I need to turn on here on my value column? Well, is the question, how long does it take for that cold liquid to warm up to the environment temperature? If that was my question, I would turn on heat conduction in solids or radiation. But that's not my question. My question is more about free surface and nucleation sites. So let's focus on free surface. So starting with free surface, I hit that checkbox, and I immediately get this pop-up about time dependency, which makes sense. We're watching a glass go from empty to full, so things are changing with time. So I do need to factor in time. So I hit OK, and that turns on time dependency. Now my question is, how long do I want to watch this glass fill? Well, like I said, I overestimated the fill time with 1 gallon per minute. So I'm going to keep a pretty low fill time here of about 2 seconds. Now my next question is my output time step. As SOLIDWORKS goes along the calculation time, let's say this is half a second. Here we've got 1, we got 1.5, and then we got 2. As we're saving certain segments of time, we're getting a full set of data for each of these moments in time. So that could very easily be a large amount of megabytes. So I want to be careful about just creating a bunch of sets of results, taking up hard drive space for things that I don't necessarily need. So what do I truly need out of this analysis? I want to know how the nucleation sites are created over time. And I'm curious on what the final result looks like. So I don't necessarily need specific time steps like this to be able to get a look at the nucleation sites, all right? So I recommend, and this is a Shivaniism, this is a me thing, having that not create individual outputs for particular time steps for this kind of setup, for this scenario. Last but not least, gravity. If I just have this liquid injecting out into this glass, but with no gravity, it's going to fly out into outer space, like we're on the space station. That's not what's happening. It's around gravity. Z direction, is that correct? Looking at my coordinate system, no, that is not. That's in the wrong direction. So I'm going to use a cut and paste to move that to my Y component. Now, as I take a look at my model, see that orange arrow? That's pointing in the gravity direction, which is not correct. Next, I'm going to pick my air, of course, and then my liquid. Now, I don't have some sort of beer or fuel in this list, but I could certainly make a custom fluid if I desired. Since this is my first pass at an analysis, I recommend using a predefined fluid because we know there's no mistake in that fluid, right? No human error. Once you're sure that first pass has worked, then please feel free to use a custom material. All right, I'm going to go ahead and pick both, make sure they're immiscible and chosen as my default fluids. I hit next. I get to this panel. Adiabatic wall means no heat transfer through the outside walls of the system, and I'm assuming smooth walls as well. And then my last page. The wider environment is at 1 atmosphere and about 20 degrees Celsius. There's no airflow over the structure. And then, of course, my initial condition. The whole thing starts as only air. Makes sense. I'll hit finish. I'm done with the wizard. Now, immediately what happens is in my flow simulation tab, that project that I created is now docked underneath my configuration. I have a tree here of things that I can now add to the setup. If you don't have the same things that I have, just right-click on Project and go to Customize Tree. You can always add more things. But don't feel like you have to do it through here in the tree. You're totally welcome to do it in the command bar or through the menu as well. It's all personal preference. My personal preference happens to be the tree. Starting from the top, I need to edit the computational domain. This domain is where we're going to be meshing the fluid. So all of this air is getting calculated, and SOLIDWORKS flow simulation needs to figure out where that air is moving. Since the critical thing I really care about is inside the beer glass, it's unnecessary to be calculating this much air. So I'm going to edit the computational domain and shrink that down to something a little bit more reasonable. And I'm just eyeballing this. You could certainly do this with exact numbers in the panel here on the left. So that's first step done. Once I'm okay with that computational domain, I right-click and I hide it just to get it out of the way. Next step, fluid subdomains. Not necessary for this setup, so I move on to boundary conditions. Now this looks like a complex column, but it's really quite simple. It's just me inputting the flow rate. I talked about 1 gallon per minute being my flow rate, so I go find inlet volume flow, and I input that 1 gallon per minute, right? But now I need to pick a face for that to get injected from. So I need to go select an inside face on that tap. I'm going to use select other to go find that face. Perfect. Now 1 gallon per minute will be constant over the 2 seconds I applied my analysis. That's not necessary or required. If you do have a variable rate that this can pour out, hit the FX or dependency icon next to the value. And as I hit this drop down, you'll see I can change this. So I could say, for example, starting at 0 seconds, I've got a flow rate of 1. Up to 1 second, that's going to stay 1. But as I go to 2, that's going to taper down to 0. And if I take a look at my chart, we can see how that is now filling my structure. So feel free to customize this however you need to. Now I'm not ready to hit OK. I almost jumped the gun. Let me scroll down. There are other options here in this list. First up, thermodynamic parameters. If I want to represent that this is colder than the environmental temperature, I need to go ahead and type that in. For example, 0 degrees Celsius. Next, I need to override air. Right now it's injecting air into the system, but I do want this to actually be my liquid ethanol. At that point, I am done setting this up. I can hit OK. My boundary condition is complete. Next, moving on to goals. This is not a required part of the setup, but I do recommend it. This is the area where you ask yourself, what is my biggest question? What am I trying to answer? What do I want numerical results for over time? For me, for filling this glass, the most critical thing is figuring out where those nucleation sites are. That's a visual result. And then how much energy they have, how much turbulence they have. So it sounds like a turbulence parameter I need to be monitoring. So I right click on goals and I get all these options. Now I'm trying to figure out turbulence throughout the entire glass. So that's a global goal, entire domain. I go find turbulence and I'm going to go ahead and grab energy, max energy in the system, measure it for me over time. Now for other scenarios, like filling of a tank or mixing of fluids in a tank, it could be important to track the mass fractions as well of the two miscible fluids. So for example, mass fraction of air and ethanol, you could grab the bulk averages for. It's not terribly necessary for this setup, but like I said, other examples with free surface flow might need something like that. Great. Now that I have my goal set up, I do need to go look at mesh. Earlier in my PowerPoint, I talked about the volume of fluids method and how SOLIDWORKS was finding the ratio of the two fluids in each cell. Logically, that means the smaller I make my mesh cells, the more granular and detailed and accurate my results, especially for free surface. So I do want to make the mesh elements smaller inside the volume of the glass. Now I have two ways I could do this. First of all, I have to go into Insert Local Mesh. Now the first way, I can create some sort of geometry that encloses the glass using one of these cuboids, cylinders, or spheres. Or I stay here in my first icon, flyout tree, and navigate to a custom solid body or part file that I created that contains the volume that I want to refine. So of course I have pre-created a solid volume that's filling the entire glass and a little bit above as well. Right now, flow simulation thinks that solid volume is totally solid and metal, for example. There's no liquid that's going to get in there. So I need to be sure to tell SOLIDWORKS to disable solid components, to let fluid flow through them, to just use this shape as a method for meshing. Now I could talk about mesh and all of these options for an hour, easy. So to keep this simple for the training session, I'm going to start with how I start most people off. And then if you need more, please feel free to reach out to us directly. We can always go into detail on your mesh. So the way I start people out, let's take a look at these two slider bars at the top. We have fluid cells and we have partial cells, or fluid solid boundary. Okay, sure you could figure this out, but what's the difference? I have a cell out here in space, and I have a cell out here in space. This one here on the left is a fluid cell, because it only touches fluid. This one here on the right is a fluid solid boundary cell, because it touches fluid and solid. So, what do I need to refine? What's most critical? For an accurate volume of fluids calculation, I need small elements touching the fluid inside that glass. So that sounds like fluid elements is what I need to define. So I'm going to go ahead and bump this up. Now, how many times should I do that? Let's take a look at this initial mesh. This is the default. This is level 0. Each time I bump this up one level, that is forcibly changing the elements by cutting them in half. So it's taking the cube and cutting it into 8 cubes. Take it out one more time, and then of course it just does that again for each of the cubes in that area. So very quickly, this can blow up to something very small. So please be careful about just taking this up to the 7, 8, 9s. That could be very dangerous for solve time. Generally, my first pass calculations are in the 3 and 4 range, okay? So I hit OK on that, and I now have my mesh. My next step before I run it is to make sure my mesh is good enough. So I'm going to right-click Mesh and Create. Run that on my personal computer using my 8 cores. Now that is done, go ahead and close that. Take a look at the mesh. I tend to use cut plots and surface plots. My cut plot shows me my mesh, hit OK, and I see the refinement that I did in that glass, see inside the volume of that glass. That's good for a first pass. I'd probably want to make that smaller for future analyses. But what else am I seeing here? I see a lot of refinement around the tab. I didn't do that. There is some automatic refinement that comes automatically with the solver. And it's here in this global mesh category. And I love this. In a past life, in a past software, I spent about a day setting up a mesh just to run an analysis. So the fact that I was able to do this in like 3 minutes just blows my mind. At this point, I am ready to solve this. It does take about 20 minutes to solve, so I am not going to solve that live. I'm just going to go and jump to the ones that I've pre-solved. So I did go ahead and run this calculation where I can look at results like so. There's the mass fraction of ethanol at the last second mark. I seem to stopped it at 1 second. If I zoom in, I can kind of see some of those nucleation sites and bubbles, but maybe I want to see that changing over time. Now, if I do, I have to have remembered to turn something on before I ever ran the calculation. And it's an input data. Right-click there and go to Calculation Control Options. Saving tab. Here, we take a look at the Transient Explorer here on the bottom. This lets me save incremental visual results for every single iteration throughout the entire calculation. Because this can quickly take up a lot of file space, we are careful to only choose results that we really care about. So for me, I chose mass fraction of ethanol, for example. Great. So now that we have set up that gives me access to the Transient Explorer by right-clicking on results. Go to Transient Explorer. This is my results changing over time. You can see quite how wild that gets at the 0-degree angle. I definitely wouldn't want to drink that. Now, having set that up and spent the time creating that one project, I can duplicate my efforts in 2 different ways. Way number 1 is to use the parametric study option. You can do that through tools. I'm going to go the fast way through right-clicking on the project name, going to parametric study, and then from here, choosing what type of optimization I want to do. For example, I could say, SOLIDWORKS, you change the angle of the glass to whatever you want in order to minimize the maximum turbulence value. Or I can say, SOLIDWORKS, I'm going to tell you which dimensions to change. For example, the dimension of this angle. And I will tell it to change to certain amounts like 15, 30, 45, 60, which goals are the most important to track, and then run a series of scenarios, logging all of that data for me in a very simple table. The results of that would look something like this. Here's my 15 degrees, my 30 degrees, my 45 degrees. And I've got my numbers produced by each one, kind of laid out here in a table format. And I can compare them all side by side and make decisions from there. Now to show off another way to do the same thing, I will show you how I did this with configurations. So, between 0, I just created different configurations of 15 degrees, 30 degrees, 45. You can see that's changing there on the right-hand side. And then to duplicate my setup, I right-click on this project, I hit Clone, and I'd be sure to hit Select, and then just hit the checkbox on all the other ones I want to copy that into. Bam, so easy, I have duplicated all my efforts, and now it's just a matter of going to Tools, Flow Simulation, Solve, and then Batch Run to run all of those overnight or over lunch, whatever my preference is. Okay, now that I have run all of them, how do I compare my results easily between them? Well, inside of Flow, I've got Compare Tool, where I decide to compare like the turbulence example. I pick which studies I want to compare it against, hit my Compare button, switch to my Turbulence tab, and then I can look at those side by side. Now this is just the visual results. I could certainly do this with numerical results as well. Seeing these turbulence values side by side, it does become obvious that 45 has less turbulence than 30, which has less than 15. And then I ran a 60 for interest's sake and found that even less. With these visual results, but also the turbulence values I get from it, that leads me to believe that the best way to fill this glass would be to start at something like a 60-degree angle. And then near the end, in order to create some foam to hold in the carbon dioxide, tilt that glass up to about 30 degrees. Now that's just a fun example of free surface flow within SOLIDWORKS flow simulation. We do have a tank sloshing webinar on August 18th, 2020. This is going to cover the turbulent energy within a tank and how long it takes to dissipate depending on the baffle design within that pressure vessel. With that, I am going to pass this off to Jeff Lunderman.
My portion tapping into plastics. My whole career's been in the injection molding industry. I am application engineer for GoEngineer, going on a little over 3 years now, concentrating on the injection molding simulation and also anything that has to do with molding and mold tools, and also general SolidWorks model building and all of that. So like I said, when we started this project, started out pretty basic with a couple of ideas of what we wanted to do with some things. And like I was saying, our first model's from SolidWorks CAD. Our next model, we can take that same model. So this is the same model. All we did was run it through SolidWorks Visualize to get a good visual rendering of the part without even having to have the true models in hand to take pictures and things like that. And this led us down another hole. We're going to do this presentation for live people, right? So we needed a prop. Well, to get a prop, we can take our models and turn around and 3D print them with our Stratasys 3D printers. So we're printing the handle, in this case with the Stratasys J50 object printer. It's printing full color. Imagine like an inkjet printer, but you're just stacking the ink on top of itself to make a 3D image. So it's a photo-cured polymer that basically you stack up. So I'm able to go in and print them full colors, pick the colors that I want and all of that. So we did those as kind of two parts, the spigot and the handle. And then we also have, we want to show the FDM side. So fused deposition modeling, we have those printers for Stratasys 2 that we carry. And we're creating kind of an assembly portion. So we printed the black part, printed the gray parts, and then we started printing the little green part, and that kind of led me down another hole. And I said, well, wait, I need something that's injection molded, so let's make our GoEngineer logo, our little GoEngineer bug. We're going to injection mold this part. So that's where we go and start looking at the tools that we have in SolidWorks to create all of these models and everything. So our first tool that I used, I have to create a mold. So of course, being in injection molding, you're going to create a mold. SolidWorks has mold tools inside it. So we're able to go through, run a draft analysis on a part. So a molded part has to have draft, so it'll come out of the mold. It won't get stuck. So the mold tools has a draft analysis. If you're working with a SolidWorks part file that has a feature tree, so you're creating the SolidWorks part file in the feature tree, you can add draft with your extruded boss and base functions. If you're working with an imported model, generally people that are doing mold builds, mold builders, mold designers, things like that, a lot of times they get an imported model, a step file, or a Parasolid model from a customer, and then you don't have a feature tree and you need to add draft. So the SolidWorks Mold Tools has the draft function where we can go in and pick a face and add draft to that face. So let's jump over into SolidWorks and look a little bit at how that is done. So I've got a model. Of course, this one was created in SolidWorks with the proper draft and all of that. Mold Tools is just a tab in SOLIDWORKS. All levels of SOLIDWORKS has it. So if I were to right click on tabs, I can go to tabs and you can turn Mold Tools on or off, just like sheet metal, weldments, all of those things. So I'm able to turn that on and off that way. So the Mold Tools command manager setup, it's got some key components, things that are helpful in building molds and designing your molds. The first section, it's broken up into basically 3 sections, are some of the surfacing tools that are used. So if you actually go in and take the Mold Tools class that we have, there's a ton of surfacing in there because you're actually creating the core and cavity from the surfaces of your model. You have to make copies of them that way. But the Mold Tools actually does that automatically for us in some cases. The draft analysis, so the way the draft analysis works, if I come in and I select a planar face and I set the draft direction, and then I can pick what level of draft I'm looking for on the model. So if I change that to 5 degrees, we see some of these have a draft angle, but I can actually hover over them and it tells me what the actual draft is on that part, which is kind of a cool tool. It'll give you what the angle is based on that. So if you run a draft analysis, everything's fine on it, then our next step, we would actually have to come in and scale our part up. So I'm going to roll through my feature tree and kind of go through the steps of this. So when we scale a model, if I edit the feature, we can scale about a centroid or about origin or a coordinate system. You can tell it to scale up a particular uniform scaling amount. So if we're scaling up 3%, you're scaling up 1.03. You're kind of giving it this scale factor. So that scales your model up. That's the first thing you're going to want to do before you start designing a mold, scale that up. So then our next section in the Mold Tools is this section up here. So we create parting lines, shut-off surfaces, and parting surfaces. Kind of follow left to right across it. The first one I want to do is create a parting line. So I've already got these created, but I'll kind of just open them up and show you the steps. So basically when you're doing a parting line, you're redoing the draft analysis again. So picking the same face you did in your draft analysis, but what this is going to do is it creates your parting line around your model at the core, at the positive and negative draft is where it tries to create this. So it'll go around and select all those edges and automatically pick all your parting lines. Some more complicated parting lines that may jump up or down, it may have trouble grabbing some of those. You may have to go in and manually do, but for the most part it's pretty intuitive because it's trying to just split between the negative and positive draft. And we get this message that tells us our parting line's complete and it can be separated into core and cavity. If we had holes in our model, it would tell us it's complete, but then we would have to go in and add shut-off surfaces, which would be the next step. So basically shut-off surfaces, you're closing in holes in the model that would allow plastic to move from the core side to the cavity side. So you're basically just shutting off holes that are in your part. So our next step, after when we have it ready for a split, we have to create our parting surface. So our parting surface is really creating the face of the mold, but with a complicated parting line like this, it's not just a square block. It tries to throw all these surfaces in. It's not a really good clean surface. You see we've got things that overlap and all of that. So within the parting surface tool, we're able to tell it if we want it to try to knit everything together, knit all surfaces, or not. If I choose not to, that leaves them as individual surface bodies. I can go in and actually delete some of these out and just utilize the ones that I want and create new ones manually. So that's what I did in this case on this model. And once you've created your parting line and your parting surface, your model starts changing some. If we look at our feature tree, we have our solid body, which is our original model, but the system creates core and cavities folders. So all of my parting surface bodies, since I didn't knit them together, it has them all separated here. And then I have my core surface body and my cavity surface body. Let's just look at one of those. I'm going to isolate it. So it's actually just showing the part that the green part, which would be my cavity surface. The core surface, it always colors red. That's one of the things to look at when you're doing the draft analysis too. So it's created, basically this is a copy of the faces from my part model that represent the cavity. So the core would obviously be, the red section would be opposite that. So what I had to do next to clean this up, I deleted those surface bodies. From the surface bodies folder, I deleted the ones that I didn't want out of there. So it leaves me with something I can work with a little better. The next step that we have to do is go in. I had to go in and fill in the rest. So I created some surface fills using the surface filled surface command from the command manager. I put a couple of sketch lines in and filled in the surfaces around the model for those big areas. So that closed in those. Now I'm seeing I'm able to create more of a face that I can utilize to create the face of my mold. So in the next step, I have to close in these areas here. So these would be more like shut-off surface areas, but I can also have them be part of my parting surface since they're the face of the mold. So I had to go in, I used the lofted surface on these. So I was able to loft the edge of this surface across to the edge of this surface and use this curve as a guide curve, how the lofted surface works. So I did that for all three of these. More surfacing tools, like I said. Mold tools is really heavy surfacing. So once I got that, then I have complete edges around the other holes. I can go in and just select the edges of the holes for create another filled surface. So that gives me all the surfaces I need to create my tool. So to make it easier on my folder to understand my folders up here more, I knitted all those together. So now I have just one surface that represents the face of my mold. So the next step, if we look at our mold tools, our next step is to do the tooling split. We've got our parting surfaces and everything like that. So to do a tooling split, basically what we're doing is creating the core and cavity side of the mold using a sketch that we create on the parting surface. So basically I just select the face of the parting surface, start a new sketch, dimension my sketch that's the size of my mold insert. And once I do that and have that in there, the tooling split command, open it, then I've got the option to set my block heights. So we can drag them to wherever we want, or we can put in a specific size. Maybe I want both of them to be exactly 0.75. And if you notice that the core, cavity, and parting surfaces are already populated. So our core surfaces are populating out of the core surface bodies folder. So it's automatically going in there. We're not having to go in there and choose these things. And the parting surfaces also, because they're in these folders here, automatically populates those. So it really makes it handy and a lot faster with going in and selecting those. So now if we look at our feature tree, it's changed again. We have all of the surface bodies, but now we have 3 solid bodies. So I'm just going to hide my surface bodies so we can see just my 3 surface bodies. I've gone in, I thought I'd create an exploded view of my, so now I have a multi-body part. Basically there's three solid bodies, one that represents my molded part with the scale, and then I've got my mold cavity and core sections that represent that part of the mold. So to do this, our little bug mold that I created, I used these tools to do that. We can take these solid bodies now. Typically, an injection mold is a big assembly of a bunch of parts. Well, we can actually take these solid bodies. If I right-click on the solid bodies folder, I have to close my... If you ever create an exploded view of a multi-body part, always remember you need to collapse it before you can do anything else in your feature tree. So I'm able to go in and save these bodies out. Since I've gone in and I've named them, so you can rename the bodies in your feature tree. Since I have named them, when I go to save my bodies out, I can click on this little box here, and it's going to automatically populate my A site insert, my bug part, my B site insert. And I also have the option at this point, I could actually even create an assembly of all these inserts to start working on. So what I did, once I got all of these parts, I went in, took those parts, made some additional cuts, added some guide pin areas on my parts, added some nut holders. You can see I also added little vents in all of that. So that's all done through SOLIDWORKS. I turn around, send my SOLIDWORKS file into GrabCAD print, then print my models out on the J750. So now I have little molds that I can mold my parts with. In our Houston office where I'm located, we actually have a little hand injection machine, so it'll melt the plastic for us. Not a lot of control over our filling, but we're able to go through and actually injection mold these parts. So I've got my injection molded part now. What I wanted to do is look at, okay, I'm going to mold this part. I need to run simulation on it to see how it's going to fill. I need to look and see what the pressure that is required to fill this part is going to be, so I make sure that I've got the proper gate location or sprue size to allow my little press to have enough pressure to pull to fill this part. So that's where SOLIDWORKS Plastics comes in. I've got the SOLIDWORKS Plastics simulation software. Plastics, it's in 3 levels. Plastics Standard was created more geared toward a part designer. So for this simple little bug part, that's kind of where I'm standing on that one, because all I want to do is see if it's going to fill or if it's going to short shot. I want to see where my air traps are, and also I want to look at the sink marks to see how this part's going to appear when I get it out of the mold. So these are things I can look at before I even build the tool. But we can see even on this little picture, we see the sink mark on this part. Looks almost identical to the sink mark showing up on my model. So like Shivani walked us through setting up a flow simulation, I'm going to walk through the same thing with plastics on setting up this simple simulation. Then I'll show you actually the full extent of doing a simulation in Plastics Premium. So just like the flow simulation package, SOLIDWORKS Plastics is an add-in. So we would go in to our add-ins and turn it on, and then we get our SOLIDWORKS Plastics tab. In 2020, SOLIDWORKS changed the workflow for plastics to make it more like the other SOLIDWORKS simulation packages. So just like the flow simulation, Shivani had to come in and tell it, I'm creating a new study. So this is the first thing we have to do on a plastic study. And when we do this, we can go in and tell it the name of the study, we can name it, and we have choices of different options of what we can do with the system. We can run a single material, which in this case is what we're doing. And we also have a choice of solid or shell mesh. So a solid mesh will mesh the outer faces of your part and then actually mesh internally also with a tetrahedral mesh inside if you choose the tetrahedral mesh. A shell mesh is basically going to mesh the outer surface of your mold and then interpolate what happens to the melted plastic in between those surfaces. It solves faster. It works great for thin-walled parts that are uniform thickness, but when you start adding different thicknesses of parts, adding ribs and cores and cavities and all that, it's more beneficial to run a solid mesh. So we'll set this one up with a solid study. So once we start our study, we've got the way our plastics manager tree works. Basically, we're just following down the tree, and as we start adding things in, we'll see it starts populating with more things, more items to fill. The first thing we start with is our domains. I created this part as a multi-body part, so I have the runner system separate from the body. So I can tell, typically when a part comes out of the mold, you're going to clip the sprue or runner off, and then it's going to finish cooling on the table. So by separating them, we have the option of leaving these out of the warpage study. So our first step that we have to do is we need to, if I right click on it, I can tell it that's going to be my runner, and then I can select that. Obviously it's my cavity. I can tell it's the cavity. So those two things are set. Now we have our option. What do we have for boundary conditions? This is another thing in Plastics 2020. They added more boundary conditions that are geometry based, so we don't have to go through and reset these conditions every time we mesh our model. So in this case, we're going to set our injection location. It's going to be on the end of the sprue, so I can select that base. We can also select based off of a point on our model, so just a 3D sketch point. So my injection location set, and now we have to mesh our model. So I have different mesh types. Tetrahedral hybrid is what I typically use. We can run a hexahedral, which is basically working with blocks, more like the Shivani's flow simulation does. I'm going to use tetrahedral hybrid to show you that. Once again, the meshing steps in a simulation are important. The way we mesh the models in SOLIDWORKS Plastics, I feel, is pretty simple, straightforward. If we run a uniform mesh on a part, say if I want to run a uniform coarse mesh and I create the mesh, we see it doesn't capture the geometry very well. The round surface here and my radiuses on the edges aren't captured very well. I can reset that. If I turn it all the way over to fine and create that mesh with uniform, it looks better, but it's still not catching a lot of that. Our estimated triangle size is increased greatly. I could use curvature-based mesh, and I create with a curvature-based mesh all the way over to fine. And we see it captures my radius is a lot better, everything's a lot cleaner. So when we told SOLIDWORKS that this was going to be a runner, it actually refines the mesh in that area better than other radiuses on the model, because that's one of the key aspects to getting a really good simulation of the plastic flowing through the runner, catches any pressure drops or any of that really well. So that meshed the shell mesh. The next step is going to mesh our internal mesh for the tetrahedral hybrid. So a plastic simulation, while it's meshing, it generally takes, it didn't go to where I wanted it, takes your shell mesh on the outside, and what we're looking for on the inside with the tetrahedral hybrid, the most accurate results in the plastics comes by having like 5 mesh elements through the thickness of your part. If this were all tetrahedral, we wouldn't be able to accomplish that very easily, especially in like this thin section. By running a hybrid, what it does is it automatically extrudes a couple of layers on the outer face and then fills everything inside with the tetrahedral. So in this case, we actually have 6 mesh elements going through the thickness, and we still have the same amount going through the thinner sections. So it gives you good, accurate results. It keeps your element count down, so it solves faster. So now we've got our mesh set. Next thing that we have to do when we come through, we set our material for our part. We can come in and open the database. There's over 4,000 different materials in the SOLIDWORKS Plastics database. They're also actually adding, the development team for SOLIDWORKS Plastics is working with major material suppliers right now, and they're going to be adding more materials. They were talking about being well over 8,000 materials going in. So they'll be cleaning up some of the ones that don't have all the data needed for some of the results and getting rid of some of the duplicates, but they're also adding way more materials that are out there in the marketplace now. So I'll just leave that as a generic ABS. Then finally, we can come in and set the process parameters. Say I'm a part designer, I don't know anything about injection molding machines, I don't know how to set any of these things. Well, the fill settings are basically when you're running plastic standard, all you're getting is the filling analysis. That's all we're looking at in this case. The filling time is based on the part your part volume and the materials that you selected, so it automatically calculates that. Your melt temperature and mold temperature also default based off the material you chose. So you don't have to know what these settings are. Clamp force limit is a default of 100. It's not going to prevent anything from solving if it goes over that, but it will give you a warning. And our injection pressure limit basically is to see what injection pressure limit the machine would have to have. So there's no way with my little hand press I can hit an injection pressure limit of 100 MPa. So this is one of the key things I wanted to look at too when I ran this analysis, was making sure my injection pressure limit was really, really low. But you can leave that at 100 as a default to get started on your settings. And then we would actually go in and run the analysis. So I have got this one already run. I can switch to that. And just like Shivani had on her flow model, she had all of these different configurations. Plastics kind of works the same way, but instead of cloning a copy, we duplicate a study. In plastics, if I were to choose to duplicate a study, I'm specifying my configuration name right here. So let's look at our flow results really quick so we can see. I can turn on my clipping options so I can actually see inside the part as it fills. So I can see the filling of my part. And one of the results we get are sink marks. That's another one you saw the image of previously. Another important one, if you're looking at a part design and trying to analyze the part design, is looking at the cooling time. The cooling time is the majority of your cycle time in an injection molded part. So if you can design your part that has a low cooling time, it's going to reduce your cycle time. It's nice we've got the ability to run a clipping plane on our part so we can find the areas of our part that have a really high cooling time. So it has to cool for 41 seconds because of this thickness. That's also probably the cause of our sink mark. We could actually come in and maybe core this out or thin it out, reduce our cooling time, which will also reduce our cycle time and our part cost. So the flow results are what you get with plastic standard. The packing phase are what we get with Plastics Professional. So we actually get to add the packing phase. So after your part fills, Then your injection molding machine switched to the packing phase, so it continues to hold pressure on the melted plastic until your gate freezes off, basically. So until your sprue freezes off, you can hold pressure on it, and that keeps the pressure on the plastic as the outside of it actually cools. So some of the results that I like to look at in the packing phase are, I like to look at the density. If you have areas of really low density inside your part, it's not packed out well, and it also could mean that you're going to end up with a void in that area. And we look at our temperature end of packing too. So if you have a temperature, if it's actually at the end of the packing phase, so you're not able to hold any more pressure on it, and you still have temperatures inside that are higher than the melt temperature or at the melt temperature, you still have molten plastic inside your part. You're gonna have to hold it in the mold longer to cool it off. So that was part of the cooling time. Oops, I got out. And then plastics premium is where we get our warping results. So we can run a warp analysis without a cool study. It's basically the best case scenario of your warpage. You'll not see better shrinkage or warpage than what you see if you run it without a cooling analysis. So without a cooling analysis, the system is assuming that the mold is all one temperature. Whatever temperature you set it at, it's all one temperature. In the injection molding process, you've got cooling fluid or water running through your mold. You're cycling this hot plastic in and out of the mold. The mold opens and closes. Sometimes it's open longer than it's supposed to be if it's not running automatic. Then it closes. So you've got these cycles of heat going through the mold. So you're never going to have a completely uniform mold temperature, and that's where the cooling analysis is important when you start looking at warp. I'm going to change the deformation scale on my warp just to make the animation a little more dramatic. But you can see how it shrinks in. We can actually look at shrinkage in different directions. We can look in the X, Y, and Z direction. So maybe you're looking for flatness or warping in your part in a particular direction. We have the ability to go in and look at those. We can also use the measure tool and measure your shrinkage or measure your warpage, measure sink marks, all of those as well. In SOLIDWORKS Plastics Premium, everything that you can do in SOLIDWORKS Plastics on one part. Remember I said we had to have a multi-body part. So I have my bug insert. So I've got our plastic molded insert that we just got out of the mold. I've got a metal insert in the end. It's a threaded insert. And then my handle, so this is going to be molded out of one plastic, and then I have a clear overmold. The way those two-step molds work, we would mold the insert and the bug insert and overmold the plastic around it, and then basically that mold opens, the cavity rotates around and closes again, and then it injects the clear plastic over the outside of it. While that's being injected, it's also injecting another part on the other side. So in a plastic study that has all of these parts, remember our other one, we had 2 domains. Well, in this case, to set up domains, I can come in, I could even have a runner system, which I didn't do on this one. Cooling channels in the virtual mold. So my first step was to come through and assign all of my bodies. So the first solid body, if I right click on it, I can tell it it's an insert. So I've got my insert, my bug insert, my cavity. So this is the overmold cavity. The handle, this is my first molding. I have my insert down here at the end. It's another insert. And then my cooling channels. So the way my cooling channels work, I can turn on cooling channels visibility. We can see these based on sketches. So I created the sketches. They can be 3D sketches or 2D sketches. Each sketch segment has to be, or each bend in the line basically has to be a separate segment. So I can turn on my cooling channel visibility, and we could edit the definition. So you tell it what diameter it is, and you can also tell it if it's a baffle or bubblers. We can set up baffles and bubbler tubes in there as well. So I had to do that for all of my cooling channels, and then also the virtual mold. So that's another domain that we add. So when we do the virtual mold, it's very similar to what Shivani showed us. With sizing it, we can go in and put a specific size, or we can actually drag that around for the mold. Typically a mold is going to be a specific size, so you could go in there and enter that information. So then we'd have to go in and set injection locations. So with this model for multi-injection, so remember we're molding this part of it first. We're molding the solid body, the darker plastic first. So we have to set up that injection location first on our model. And then it rotates to the other cavity and does the other injection location. So we set up 2 different injection locations. Our other boundary conditions we set on this are our coolant inputs. So I can go in and show those. So with the coolant input, you're going in and you're putting in your ins and outs. So your coolant in, your coolant out, specifying the flow rate and specifying your flow rates and specifying the temperature of the fluid going in. So it takes those into account. You put the flow rate in because it's going to check to make sure you have turbulent flow. Your turbulent flow through your water lines is more efficient at removing heat than a laminar flow of the fluid. So it'll actually check for turbulent flow when it's doing the solve, and it'll give you an indication that you're not achieving turbulent flow. So it's really nice to be able to see that and know what pressure level you have to run it at. So once we set up all of our boundary conditions and everything, then we mesh our model. So I can turn on everything that I've got on there, right? So I've got my water lines, I've got my mold, I've got my inserts meshed, and I've got my part meshed. So we're able to mesh all of these different items. I can set my polymers, so I set 2 different polymers. Since I have 2 different injection locations, I can set them separately for different materials. The coolant has a database too, just like the polymers, so I can tell it if it's water or if I'm running ethylene glycol or any of some companies make different coolant fluids if you're running extremely low temperature so that it doesn't freeze up. Or some companies run hot oil through their molds if they're running a high temperature plastic like PEEK or something that runs where you have to heat the mold. And we can also assign mold materials as well. So this one, and I can set as P20, just a basic tool steel, H13, A2 tool steel, all of the typical industry standard steels are in there. And the inserts are the same way. The insert database, I can choose a polymer or I can choose a metal. If I choose polymer, I'm choosing from my plastics polymer database. So remember, our bug is molded out of a particular material. That insert is going to be that particular material. Once we get everything set up, we've got additional settings. Remember, previously we only had fill, pack, and warp. The warp setting is a 2-step. It's you set the ambient temperature, so the warp analysis is actually taking the part from the mold, sitting it outside the mold on a table at whatever the room temperature is or whatever temperature it's cooling at, and finishing the cooling process and warping process down till the temperature reaches that ambient temperature, so till it levels off with the ambient temperature. And then we also set our gravity downward direction. So which way is it sitting on the table? Which way is gravity pulling on the part? And finally, we have cool settings. Also, if we set up a cooling analysis, if we set water lines, the cool settings pops up. If we don't have water lines, we don't have cool settings in our process parameters. So it's pretty intuitive that way. And finally, we run the analysis. So you notice with all of these things set up, we have all these different choices of what we want to run. Typically, you'll always run the cooling analysis first. So it goes through and cycles through your mold, takes into account for the temperature of the plastic going through, the fluid flow going through, all of those things, and does the thermal analysis on the mold system. And then we're going to run flow, and then pack, and then warp. So we have the choice of going through and running all 4 in a row. Let me turn on my mold visibility. These are already run. I want to look at my cool results first. So one of the things I can look at is look at my mold temperature, or my cycle average mold temperature. I can look at areas in my mold and look for hot spots where I may not be cooling the mold properly. I'm not getting even cooling in the part. So we're able to look at those things. We can look at the mold temperature at end of cooling, so you can see how the mold is heating up. If I hide my mold visibility and just look at cooling channels, I can actually look at my the cycle heat loading on the cooling channels, or the average heat flux. So how much heat is that cooling line having to remove? I can look at the pressure of my cooling system. So my water pressure going in is flowing higher than my water pressure coming out. Do I need to go through and adjust any of those? Do I have areas where my water pressure is too low? We can also look at our water velocities. So you can look at the velocities through the bubblers, things like that, to help determine your turbulent flow and all of that. So these are all nice cooling. And you also get a part cooling time as well from this analysis. So this is overall after all the cycle and everything. Some of the nice plots that we have access to, the XY plots, one of the ones that I use the most, we have access to in Plastics Professional, is the part mass plot. So it's basically showing you at what point during the cycle, so this is during your filling phase, and then it switches to your packing phase on your model. So at what point during the cycle does your part quit gaining mass? So it's almost like a short shot study, or a gate freeze study. So it's telling you, giving you a window. So I can add some more packing pressure up to 6 seconds that would help pack this out and get rid of some of the sink marks. And it's cool on an analysis that has the co-injection or 2-part injection. You've got 2 sets. This is the first material, and then this is where the second one came in. So the packing phase of it as well. We've got options of looking at our melt front flow rates. Say that 3 times fast. So I zoom in on those. So you can look for your flow rate profiles. If you get stall areas in the flow rates, it may end up creating flow lines on your part, things like that. So you may look for areas where your flow rate drops way down during the filling stage, and maybe your material is stalling it out in that area. That's all of the story behind creating all of these parts and some of the tools that we used with our injection molding, 3D printing,
and flow simulation. Thanks for coming to this flow and plastics training session. If you're interested in other events or webinars with us, please go to goengineer.com/webinars. Again, this has been Shivani and Jeff with GoEngineer. Thanks for watching.